navigating the data center revolution. The context here is rise of AI. There are many levels of AI. We are at weak AI. Average advanced AI is yet to come. But even within weak AI, there is assistive AI, there is predictive AI, there is generative AI, there is agentic AI. The list goes on and on. And as you can imagine, all of this training and inferencing requires a lot of power. That's making data centers extremely power hungry. Just about a year ago, the US Department of Energy said that the data center energy demand will go by 3x by 2028. Just last month, they said, make it 4x. The point is, the data center demand is going up, and it is accelerating. In many places, data centers are expected to bring their own power. Speed to power is just the beginning. Cooling, water, pollution, sustainability, there are so many things to consider. This map from the National Lab of the Rockies shows data center locations and their power consumption in the United States. Big circle means more power. Virginia and Texas lead the pack. San Antonio is 1,500 megawatt. That's about 1/4 our city's power consumption. Let's take a closer look. This is County Road 381 at Omicron, about 15 miles west of here. That big boxy building, that's Microsoft AI data center. So that AI cloud we spoke about, some of that lives here. Data centers are our neighbors. They want to be good neighbors, but concerns remain. This is last week. A typical data center has generators, coolers, servers, storage, networking, all kinds of stuff. A center like this could occupy hundreds of acres, and some of these buildings could be 5 times longer than a football field. This is massive, and yet it is becoming common. So what's the upshot of all of this? Well, we spoke about massive power demand. Every bit of power that the AI servers use becomes heat, meaning the challenge of cooling data centers is just as massive. If data center is producing on-site, at some point they have to address the issue of pollution of various kinds: air, water, sound, light. Power demand comes with another angle, that is of its shape, the power quality. So data center operators have to operate within the framework defined by the governments, utilities, the public, and the corporate goals of sustainability. That's a lot to do. Enter Southeast Research. This is a complex diagram because SwRI has so much to offer to this industry. Let's begin at power, electricity. Data centers expect that the electric grid will supply their demand. The grid is limited in its generation and transmission. So data centers must produce on-site, be it for backup, be it for the main supply. And that often means engine-based generation. Engines is a core competency at Southeast Research. And so is battery energy storage, solar generation, cooling, and Southeast Research has a long-standing reputation as a test and validation house. In addition to all these established technologies, there are other efforts on campus pertaining to carbon circularity, sustainability in general, and they require more work. So in summary, Southeast Research is ready to support data centers, to provide system-level proof-of-concept demonstrations, to do component-level testing and validation, and to do R&D for that next solution. Let's look at some examples. On-site power generation typically means turbines. This is the mainstay of on-site power generation. This 16 megawatt stand is an example of SwRI working with OEMs to develop, test, and validate products. Diesel engines is another example of on-site power generation, mostly for backup. The combustion system on this 3 megawatt engine was designed and developed at Southeast Research. Maximizing fuel flexibility, improving load response, reducing emissions, increasing efficiency, all have been long-standing capabilities at Southeast Research, and they apply directly to data centers. Southeast Research is writing the new chapter, the next chapter in power generation. This is the STEP facility. Over on the left is the supercritical CO2 turbine. This highly efficient, compact, fast-responding machine is heat agnostic, meaning it can operate on heat from various sources, be it natural gas, be it geothermal, be it concentrated solar. That gives great flexibility to data center operators. We come to power quality. All right, so on the left-hand side is the load profile of a non-AI workload. On the right-hand side is the AI workload. And as you can see, that the profile of the AI workload is very dramatic. It is continuously changing with big steps, very different from the non-AI workload. A mechanical generator, when subjected to this kind of load, is going to suffer fatigue and possibly not live as long. So data center operators are thinking they can introduce batteries as a buffer between the generation and this very difficult load. Our own data from our own facility on Commerce Street indicates that batteries may not do so great in that role either. But there could be complementary technologies. We are working on that. If a data center is producing on-site solar generation, they can improve the solar output by choosing the right ground cover, and we are working to quantify those gains at the same facility as well. The power consumption of AI racks is expected to go up by tenfold in the next few years. Same footprint, 10 times the more heat. So the idea of taking the computer and putting that into a cooling liquid is very appealing, except what kind of liquid that needs to be is not known. So Southeast Research is launching a new industry program to standardize test methods and answer that question. In addition to server-level cooling like this, we need to have site-level cooling that can remove this heat ultimately. My colleagues, Eugene and Ashok, will cover that next. Eugene?
Thanks, Jayant, for the introduction and great way of starting this presentation. I know we all heard a lot about data centers, but Ashok and I will be talking specifically about the cooling aspect of data centers. And we'll get into a little bit more about what is being done and what we are doing here at Southwest Research Institute to assist the industry in this space. So cooling in data centers affects all aspects of the infrastructure, thinking about the cooling towers starting from the outside where the heat is rejected, through to the racks that are sitting inside the data centers, all the way to each individual server. There are various aspects of components that go into forming the cooling aspects of data centers. But first, why is cooling important? So if you look at the traditional data center, for all the power that comes in, somewhere in the range of 35 to 50% of that goes into cooling. And tying back to what Jayant said, I'm reshowing the graph up here, that power demand for these data centers is bound to grow, regardless of which projection you look at over the next 5, 10 years. So our goal here is simple. How can we decrease that concentration of cooling? How can we make it less, more efficient so that it uses less power? And that may give us a fighting chance to help tame the power-hungry beast that is data centers. So I'll call my colleague Ashok here to talk a little bit more about the cooling methods, and then we'll talk about what we do here at Southwest Research Institute.
Thanks, Eugene. So with regards to cooling the data centers as such, conventionally, there have been several ways of cooling data centers. What is the driving factor is the heat rejection capacity and heat rejection density. Air-cooled data centers have been around for years, but they are limited by the amount of heat they can reject. So large air handlers and fan walls can reject up to 60 kilowatts per rack. But with the advent of AI and high-powered chips, the industry has been slowly gravitating towards liquid-cooled data centers. In liquid cooling, it can be divided into several methods, depending upon whether it's direct liquid cooling or indirect liquid cooling. What is commercially used is cold plate, where the cold liquid passes through the cold plate and removes the heat from the chips. And it's a form of indirect liquid cooling. And there are emerging techniques like immersion cooling, spray cooling, jet impingement, which are not yet commercially implemented, but are also up and coming. And further, depending upon the phase of the liquid flowing through these chips, It can further be classified as single phase, which is liquid only, or two phase, which is a combination of liquid and vapor, where the heat transfer occurs through phase change. So here at Southwest Research Institute, we test very critical equipment for data centers, be it heat exchangers, which transfers the heat from the technology cooling solution to the facility water, or the pumps which move the fluids through the data centers, or several other critical components like the pressure-independent control valves or variable frequency drives, which are all implemented and critical components for the data centers functioning.
So apart from the individual components, we also do package design and package testing, because the individual OEMs will assemble all these components into a standard unit, either a cooling distribution unit or a mechanical equipment skid that will be brought on site for us to proof test. The main point and the main reason why we do a lot of testing is because these data centers are mission critical infrastructure. In a given year, a data center is only allowed to be off-site or offline for a few minutes in a given year. So ensuring that these major components can actually live up to that expectation is what we do here at Southwest Research Institute with our testing capabilities. So we don't only do performance testing to ensure that they can actually hit the rates that they are supposed to, but also ensure that they are reliable enough to serve in this infrastructure to upkeep all the various aspects, such as like your banking, your healthcare, and all other aspects that are tied to these data centers. So how do we do that? We have currently developed 2 facilities to handle these testing. We started with a medium-scale heat exchanger facility that we developed thinking that that will be sufficient, but boy, were we so wrong. So we went from something that was less than 1 megawatt to a 3 megawatt facility that was essentially upscaled to meet the growing demand. But currently, we are seeing the demand for 5 or 10 megawatts worth of heating and cooling, and that trend is just growing. So we're currently doing some work internally to collaborate with other groups to see how we can develop the next generation of testing capabilities to assist this.
So at present, at Southwest Research Institute, we are working on both the testing, advancing both the testing and the research wings of our cooling department. So on the testing front, we are currently expanding our capabilities of the large-scale test facility for the cooling equipment from 3 megawatts to 5 megawatt. That's about a 70% increase. And we're also designing the loop to meet the upcoming standards, which we're also like a part of the committee which sets those standards. On the research side of things, we are also currently working on an internal research and development project, which aims to develop next-generation cooling products, specifically through two-phase direct-to-chip cooling, which we think is going to be a big driver in the market 3-4 years down the line. And we also received a lot of interest and support from some of our existing partners for the release of the product. So to summarize what we've seen so far, at Southwest Research Institute, we are able to draw upon our experience in testing and research and impact several areas which are critical to the functioning of the data centers, be it cooling, where we are improving the efficiency of cooling right at the equipment server, rack, or the facility level. Also advanced fluid development and testing. And we're also able to call upon our experience in several other areas, such as primary and on-site power, backup power, environmental compliance and emissions, cyber physical security, and also waste heat recovery. With that, we would like to call upon our previous presenter, Jayant, and we would like to open the floor for any questions. Thank you all for your attention.
All right, we got a question right up front.
Yeah, it raises questions about what the limits are for terrestrial data systems like this. And I saw recently that Google has applied for FCC license to do 1 million spacecraft in low Earth orbit to put data systems in space. I guess I'm asking about the limits and also your comments about the space-based data systems.
So what are the limits for these data centers and in space, the limits for space?
Yeah, that's a very great question. And that's something we discuss internally as well with orbital data centers and terrestrial data centers. But for terrestrial data centers, I'll start with that portion of it. The limits are threefold currently. How much power do you have access to? How much water do you have access to? And then there's currently that is growing as a policy aspect of it. What would you be allowed to essentially put up data centers? And so it's not as simple at this scale, data centers will be stopped, is wherever you're putting up your data centers, which of these three will be your biggest dominant constricting factor? And so depending on where in the US you look, various aspects are actually pulling up in front of other aspects when it comes to data center and putting up new data centers. Orbital data centers are a great topic. I like data centers. I love space as well. Most people that know me, it's a great intersection of my interest factors. I'm hoping there to be a lot of orbital data centers. There are companies that are currently chasing that. But let's just be honest, there are also a lot of challenges that are facing orbital data centers. Sure, you have access to sunlight that can help provide power, and people say space is cool because you have access to the vacuum that you can reject heat to, but there are also challenges in actual heat rejection, and radiators are not currently at the limit where you can reject that much amount of heat. And so there's a significant R&D push currently to actually make that feasible, and then trying to drive down the cost for essentially flying stuff to orbit to make that accessible. So there's a lot of aspects at play when it comes to both of these topics.
I would also like to add to that, and the thing is, you have like free energy and free cooling in space, but if someone is able to answer whether the techno-economics make sense, the cost of launch, whether it's like significant enough to like be a showstopper, if someone is able to answer that, I think like we're like very close to like that being happening as well.
Yes, orbital.
We have a question right over here at the back.
So I have two questions actually. One is how much of your work is research and development versus testing? And secondly, these data centers are already popping up all over the place. I live in Medina County, and there's a huge concern about power and water. There's a great number of data centers that are popping up there. So my second question is how long the technology that you're developing, when will that be available to impact the usage of water and electricity in these data centers that are already there?
So the twofold question, how much of your work is R&D versus testing? And how long until your work will impact the amount of water and power available for these data centers that consume so much?
Maybe I can answer. The mindset right now at least is, let's do it first. And whatever the problems come, let's handle them later. I think that seems to be the mindset. Speed to power is the slogan. You will hear that so often, that people say, let's get started, issues will come up, and we'll solve them. So we are hoping that the work we are doing sort of will be just aligned when the issues start popping up, that we are there to help out.
To add to that as well, all of the projects that we've done regarding the data center cooling space has been all testing and evaluation projects. What we are currently doing this year is a lot of research work as well, where, like I said, like we're developing a two-phase cold plate, which we think has a lot of industry traction and we think can impact the industry as well, to reduce the sort of power consumption right at the chip level. And we hope that that's probably going to come up in the next year or two. So.
Okay, let's take this question right up here first.
As a follow-up question, I was going gaga over AI, and my young niece, on college, said, but do you realize that any one query on ChatGPT costs 14 gallons of water? Is that true?
Does ChatGPT really take 40 gallons of water?
14 gallons for one query.
I don't know, it
Okay,
depends
how
on
much-
where you start counting, right? Does it also include training? Maybe, yes, it does. But it depends on where you draw the box.
Okay, right over here.
I have a two-part question. In your diagram, you showed the cooling towers that you have. Are those internal to the building? Are they external? For one. When I say internal, are they within all the other computers that are within that area? Are they external to the building? The second question deals with power, and I know this is a big issue with ERCOT right now. Are y'all having any discussions with them? Because they're huge.
Okay, are the cooling towers internal or external, and any discussions with ERCOT?
So, great question. The cooling towers essentially sit externally to the main building of the data centers. So the heating or cooling is transmitted to them through piping. And then the cooling towers or your chillers sit outside and reject that to their ambient atmosphere. With regard to discussions with ERCOT, currently, I personally am not aware of any connections, but maybe Jayant.
Yeah, so I think we are having discussions with CPS Energy because I think a lot of the electric demand that needs to be serviced within CPS service area, of course, is coming from them. The big question has always been, if you ask data centers to bring their own power, all this equipment is worth 20, 25 years of lifetime. And if at some point ERCOT requires that they connect back to the grid, what happens to all that investment? So I think some of those questions need to be answered because those are unusual questions that have not been thought about yet. But yes, we are talking with CPS Energy, not directly with ERCOT.
And I have one follow-up question. They're talking about small nuclear
Reactor.
power supplies, and I know you are dealing with that. Is that something that you're working in contest with this?
Are small nuclear power supplies in contest with this?
Yeah, so the SMRs, I think, are the new thing on the horizon. There is some work going on in Division 1, but I don't personally know what that is quite yet. So I'll have to find out.
Okay, I know we had one last question back here.
How is SwRI trying to change the conversation around data centers? So it sounds like you're trying to manage the status quo as opposed to trying to move to a new normal. So I'm kind of curious as to how SwRI is trying to move the industry to thinking about data centers differently than what they currently do.
So
How is
I'll answer this-
SWRI changing the conversation around data centers?
I'll answer this question, it's going to be like twofold answer. So the first one is, of course, very obvious. Like we talked about the internal research project that we're doing to improve the efficiency and reduce the power consumption right at the chip level. But apart from that, there's also a huge opportunity to use the waste heat which comes from the data centers. The rejection of low-grade waste heat can be converted to something useful like district heating, or we're also in conversations with some of the ARPA program directors to sort of look into how can we use that waste heat and maybe get a desalination system out of that. So wherein you're also consuming the heat, which is rejected out, but also producing water, which is also useful. So we're in conversations into how we can use waste heat to sort of improve and sort of make the society better.
Clarity is a big topic, and I think we are showing that we have some answers that data center industry could adopt, and I think make it into an overall sustainable solution in the long run. So I think that's a conversation that we need to be having.
Okay, thank you for your time and your
Thank you.
presentation.